Good morning everyone. Today we are going to talk about anatomy of data source API. Last meetup we have talked about Spark SQL, where we talked about how to process structured data in Spark. In that talk we talked about three different APIs under Spark SQL. One was data source API, one was data frame API, and data frame DSL and SQL for processing these data. But today we are going to focus on datasets API alone. So here we are going to deeper in one of the API and also other APIs we are planning to cover in subsequent sessions. The code for this talk is available on GitHub. The link is given in the PPT. Now, if you don't know me, my name is Madhukara Phatak. I run a company called Data Mantra, where I consult in Hadoop, Spark, and Scala, and ecosystem projects like Hive, Page, and other things. If you want to connect with me online in Twitter or LinkedIn, you can go to this website, madhukaraphatak.com, and connect with me. Right. So, what is the agenda for this talk? Today, in the beginning, we are going to talk about data source API, an introduction to that. So, just to get an idea like what exactly the API does and those kind of thing. If you want to know more about what exactly is the API, you can see other videos of mine. And after that, what we are going to do is that we are going to see every part of the API and understand how to implement. For example, we are going to talk about schema discovery, data type inference, etc. etc. Okay, let us get started with data source API. Now, what is a data source API? Till Spark 1.2, the only way of loading data was input format. Now, input format is not unique to Spark, it is borrowed from Hadoop. But the issue with input format is there is no support for loading structured data specifically. For example, if you want to load JSON or CSV, you have to just piggyback the same thing on input format in order to load the schema, but there is no direct support. But from 1.2, there is one universal API for loading and saving structured data, and that API is called as data source API. From 1.2, you don't need to use input format to load the structured data. You can use this API, which has more nice properties compared to just plain input format. Now, why I say it's a universal API is this supports a wide range of structured data that's out there. For example, there is a built-in support for Hive, Avro, JSON, and these kind of things, where you, by just adding Spark SQL dependency, you can use all these sources to load or save. But not only the built-in support, there are so many other third-party packages which are available by now new site called Spark Packages, where you can integrate with any other custom source you have. For example, there are support for CSV, MongoDB, Cassandra, etc. from the community. Not only from the community, if you have a custom source which is sitting inside your company, you can write your own data source API in order to plug in and take the data from that data source. So the idea about data source API is that it gives you a clean interface to interact with structured data. Now, what is the use? If you see this picture, there are two kind of worlds we see. One is there is a wide variety of data sitting in different places. For example, there is structured data sitting in Hive, there is a structured data sitting in Avro, CSV, Parquet, maybe in your RDBMS, HBase, and etc. etc. Which means you have a lot of sources of data where they have structure. Not only that, you have different applications. For example, your Spark application written in variety of languages, maybe streaming applications, maybe machine learning applications, which want to consume these different structured data. Not only that, you have this enterprise application like BI tools like Tableau, Zoom Data, Qlik, those kind of things, who want to work with this structured data in order to do visualization and reporting. Which means you have these two worlds where there is a wide variety of sources giving you different structured data, and also there is a huge amount of applications which want to interact with this data. Now, having a connectors which are specific to each of the sources with the combination of application is too much for maintenance, right? So you cannot create a connector for different sources separately. So that's why if you see the Spark SQL or data source API as specific is kind of a middle layer which bridges these two different worlds. So if you want to consume different kind of structured data in different kind of applications, data source API helps because it's an universal API to consume the structured data in Spark. Now, if you want to know more about the data source API and how we can interact with the different data source APIs, so different data sources, you can just go through the video linked in the description. Now, in today's talk, what we are going to look at is how to build our own data source. So that's why the talk is called as anatomy, which means we are going to touch upon the different things in the data source API in order to understand how to build a data source from the scratch. Now the data source which we are going to build today is we are going to look at how to load and save CSV data. So the data source we are building is for CSV. The reason I have chosen the CSV because CSV is something which is easy to understand and easier to implement, and that is something what we use in everyday life. So there is one disclaimer here. The code, whatever the code which is shown in the presentation or in the shared in the GitHub is just for learning purpose. Don't use this in production. If you want to use CSV data source in the production, I recommend you to go through Spark CSV, which is given by Databricks. So with that disclaimer, let us see what we want from CSV data source. Now in this slide, we are looking at what are the requirements we have from this data source. So by understanding the requirements, we can see how we go about implementing these things in our data source. The first is we should be able to load and save CSV data. So this is the simplest thing. So because if you have CSV data, you should be able to load it to Spark and analyze it. And also if you have some other data source, we should be able to save it as a CSV data. The second thing is that we want to have automatic schema discovery. So one of the nice thing about data source API is that it allows you to discover schema rather than specified by the user. Most of the time we know the schema is there in the CSV as headers, right? So we should be able to look at the header and discover the schema ourselves. So that's one of the requirement. Not only that, if the user says, no, I know the schema better than whatever you are discovering, we should allow the user to override the schema also. So not only that, we should have the ability to discover the schema, we should also allow the user to say, don't care about your discovery, let me give. So that we call as a user schema override. The fourth thing is that not only we want to discover the columns, we want to also discover the data types. So by looking at the data, we should be able to say, okay, this is a string, this is an integer, this is a double. Now if you see the first four properties, they are standard for any kind of a data source. We're also going to look at a little bit advanced APIs which are there in the data source API. So one is that how to do column pruning so that we only select the columns which are required, and also we'll discuss a little bit about the filter push. So the last two requirements are somewhat advanced in terms of the API. Okay, let us start. Now we are going to build this library of data source over a time. So we will take specific requirement and we see how to implement it. Now when we develop a library, as we go along, we want to see how it is developed over a time. Right. For that, I am using GitHub tags or Git tags in order to show you how the library is improved over a time. So after cloning the data, if you go to your Git, you can see so many tags. So what I have done is that for every feature there is one tag, and by checking out the specific tag you can understand what is the state of library and which feature is getting implemented. For example, in every section in the slides I am specifying that which is the tag is used for this specific feature. So for example, for the schema discovery, since this is the first feature, we are using the tag v0.1. Now how to check out a tag into a branch? We say git checkout -b first v0.1. In this way, what we are saying is that on the clone of v0.1, so we will be looking at the specific code for this feature. Now let us go to the IntelliJ and see what is the code we are looking at. Right, before that, let us see what we want to see. Right, the first thing we are going to see is that how to use this data source API. By understanding that, then we will look into how to implement the schema discovery. Okay, so let us open CSV schema discovery code. Let us get into the full presentation mode. Okay, now if you look at this example, all the examples are written in Scala here. If you look at this example, the first thing we are doing is creating a Spark context. Then what we are doing is that we are creating a SQL context. The reason we are creating SQL context is that all the API in the data source, they come under Spark SQL. And if you want to access these APIs, you have to create a SQL context so that you can interact with them. So what we are doing is that after creating the Spark context, we are creating a SQL context. After that, we are saying SQL context load. Now the load is an universal API for loading any kind of structured data. So what we are doing is that we are saying okay load, and we are giving a package. In this example, the package is Madhukara Phatak Spark Data Source.csv. Then after that, what we are doing is that we are giving some more parameters, such as we are giving the path of the file, and also we are giving the header equal to true, which means we want to say let's take that header so that we can do the schema discovery. And after that, once we have loaded the data, which will be represented as a data frame, we will be saying df.print schema in order to say, okay, what is the schema of the global? Sorry, what is the schema of the data frame? Are you able to follow till here? Okay. Now, your obvious question will be, whenever I give this package in SQL context.load, what exactly is Spark is trying to do? How Spark knows where to look for the schema and etc. etc. So that's where we start with our first implementation. The first thing Spark look at is something called default source. By name itself it says it's a default place where Spark will be looking at. Now what Spark does is, Spark looks for a class name default source in the given package of data source API, which means whatever the package you have specified in the load function, Spark looks for a class called default source in order to start doing the processing. Now, what default source is, it's like an entry point for data source API. So, for a very easier way to understand is that it's an entry point to say, okay, let's start the data source API processing. Now, what default source should do is, it should extend something called relation provider trait. So trait in Scala is very similar to Java interfaces. So it should extend something called relation provider. What the relation provider is, it takes the user parameters, so whatever you have sent, like path and those kind of things, and turns them into something called base relationship. So we will talk more about base relationship in the next slide, but what is the relation provider? It takes the user parameters, then turns them to something called base relationship. We can also implement something called schema relation provider. With the relation provider, there is something also called schema relation provider. What it does is that it also allows us to do users defined schema, which means the user can specify his own schema, then you can override your discovered schema with that. So let us see the code in order to understand more deeper. Right, so let us open our default source. And so what it does is that it extends relation provider with the schema relation provider. So we are extending both because in our requirement we also want to give access to the user to say okay override. Now if you see this, we are overriding two functions. We are overriding a function called create relation, which takes these parameters. It takes SQL context, it takes the parameters whatever is passed as a map of string, and it returns base relation. And if you see the second create relation, including the things what we have sent in the first API, it also takes the schema. So in this implementation, what we can do is that we can allow user to override the schema so that we can say okay, don't discover, just use it. So, but both the things, both the create relation, they return base relation. Now just let us look at the implementation. What we are doing here is that first we are checking for the path, because if the path is not specified in the parameters, then there is no meaning of doing anything, so we give an error. Then we do have an option to specify separator. If you have a CSV with other than comma, you can specify, otherwise we'll take comma. Then ultimately we create something called CSV relation, which is of the type base relation. Now the obvious question will be, what exactly is a base relation? Now if you think about RDD is a collection of tuples, right? So if you think about RDD is collection of tuples. Now the base relation is, it's a collection of tuples with the known schema. Since we are talking about structured data here, most of the structured data comes with a known schema. So what we are talking about base relation is a collection of tuples with the known schema. Here the word known is important. The known means once the schema is discovered or specified, it will be same forever. So it's not like it's going to change from row to row. Once we specify or discover the schema, it's going to be always same. So base relation is a collection of tuples with the known schema. Now we have to override two methods here. The first method is SQL context, which allows us to say which is the SQL context the API should be using. The second thing we are going to return is the schema. So if you look at the API, it's a schema which returns struct type. Now the return type struct type is very similar to the schema specification in Hive. For example, if you have worked with Hive serializer, deserializer, you may be seen this struct type. If you have not seen also, no, don't worry, it's very simple. We're going to talk when we look at the implementation. So let us look at the implementation of CSV relation. Okay, so we have CSV relation with all the information we have got from the default source. Now, if you look at this, we are also extending a base relation here. Don't care about table scan, we'll talk about that later. Now if you see this, what we are doing here, so if you see the implementation of schema, the first thing we are see is that if you have a user schema, just return the user schema, which means if user has specified the schema, don't try to discover, just give it back the same schema what he or she is specified. Otherwise, what we are going to do, the implementation is very simple. What we do is that we read the first line from that file using SQL context, Spark context text file, so that we get the first line which has the header. The second thing is that we split the header using a separator, so that we get the name of the columns. Then we convert these column names into struct type. So what we are doing, for every column names we are mapping, right? For every column name we are mapping. Then we create something called struct field. Now struct type, you imagine like a C structure, right? If you have gone through C programming language, you know what is struct. Struct is just combination of multiple basic types. So struct can have integer, string, and those kind of things. Now one more nice thing about struct is if one struct can be there in another struct, which means it does allow nesting. Now if you think about structured data, you normally think about flash structures, right, where we have columns and rows. But we do have a semi-structured data like JSON, which does need the whatever we have this nested structure, right? So to allow the nested structure, we use something called struct type, which allows a struct type is another struct type. But here we are using very flash structure. So what we do is that for every column name, what we do, we create a struct field, which is a very basic field in the struct type with the field name. So that is the first parameter. The second thing is that as of now we are not really cared about the data type. So what we say is that irrespective of the data type in the file, we are going to assume like it's a string file, string type. And the third information we are saying nullable equal to true. Now one of the things in the data source API is you can specify given a column can be null or not. Now this is very important because if the column can be null, the optimizer in the Spark SQL has to do some of the things. So if the column may not be null, then it do not need to check for nulls and those kind of things. So, but here we don't know about that. We just say nullable equal to true. For every column name, we create this struct field. Then we get an array of struct fields. Then finally, this array will be wrapped around a struct type. So this is way we take the column names and convert into the struct type. So whenever we're talking about the schema, So what we are talking about this combination of struct type. Now finally we have implementation of default source and the base relationship. Now we should be able to run this example where we process this CSV data and then we will be able to run. So let us see what should be the parameters we should be giving. So we will be passing local, so that is the master path. Then we will be passing sales.csv, right? Okay, so I think there are some changes. So let us see. So let's give some time for compilation and those kind of things. I think it may fail because we have not specified the parameters. Let us give some Scala compiler to compile and generate the bytecode for us. Oh, it does have parameters. I will show you the parameters once it's executed. Okay, if you see, we are getting this for field transaction ID, customer ID, item ID, and amount paid. Now let me show you the sales.csv file. Right, so if you see this file, it has same fields. Now what we are able to do is that able to give this parameters. Okay, let me show you the parameters also. Right, so we are able to give the parameters local, that is the master path. Then we are able to give this sales.csv from which file we will be able to discover the schema. So what we have done till here is that we have able to implement default source and the base relationship in order to read the CSV data and discover the schema. So this is our first part where we are implementing data source API with some data discovery. Let's continue. So in the last section we have looked at how to do the schema discovery. Now in this section we are going to look at how to do the reading data, which means after the schema is discovered, now next we have to do the reading of the data. Now as we had seen in the last section, here what we are going to do is that we have a new tag called v0.2 where we are going to have a new code. So let us check out that thing. Okay, so now we have a new branch which has the new code. Let us look at what we want to do. Now, as we implemented schema with the base relation, now we have to implement a trait called table scan. By name itself, you see it says table scan, which means we want to read the data from a table. The naming convention is table because here we are talking about SQL, and SQL normally we talk about table, but it does allows to read any kind of structured data. Now, what it is the table scan is, it takes the data or whatever the parameter is given by the user and it creates something called RDD of row. Now, if you see this RDD of row, it looks like a collection of data, that's RDD with the type of called row, and this was similar when we talked about schema RDD in 1.2. So in 1.3 we have data frame, but earlier it was used to called schema RDD, and schema RDD used to have a type called RDD of row. So row is a type given by SQL of Spark. You think row is like a result set, which means it has all the column information with that actual data. So what we do here in this example is that we take the CSV data, we load using sc.text file, which gives us the RDD of string. Then we convert that RDD of string into RDD of row, because RDD of string is a unstructured data without any schema. But when we convert into RDD of row, what we get is data with some structure into it. Okay, let us look at the code. So if we see our CSV relationship will be improved now. right? So now we are implementing table scan, and also we are implementing serializer. The reason is that CSV relation normally will be shipped on network in order to do all these transformations. So you should be able to serialize it. So that's why we are using serializable, and also we are implementing table scan so that we will be able to read the data. Now if you see the implementation of build scan, which we have to override if you are implementing table scan, it's very simple. What we do is that first we load the data using text file. We create an RDD. This RDD will be RDD of string. Then what we do is that we get the data lines. Here data lines means the first line is a header, and we don't need that when we were processing the data, so that's why we filter out that line. Then what we do is that we take the column values by splitting the row, so which means for every row we'll split the columns using a separator. Then we convert that RDD of string into RDD of row using row.fromSequence. So row.fromSequence is a utility function. What it does is it takes any sequence and converts into a row. So what we are trying to do here is that we take a RDD of string, which will be given by the sc.text file, then we convert it to RDD of row. Now using build scan, what we are trying to do here is we're trying to take the data which is in the string format and convert into a schema which is given by the schema API of the data source. I think all are able to follow till here. Let us see how to use it. So we have an example called CSV table scan example. It takes same parameter as whatever we have seen before. So if you see, the first three lines are same, but since we are able to load the data now, what we are going to do is that we are saying df.count, which allows us to count how many things are there, and also we are saying df.collect as a list, which allows to see the actual data inside the file. So let us run this example. So it's same parameters, and so that's why I'm not showing you the parameters. Okay, it's running now. Okay, so what we are seeing here is that if you see, we have 14 rows, and ultimately we are seeing some data. Bear in mind that even though the data looks like a numbers, it's still taking as a strings, because when we have created the schema, we have specified as the strings. So what we have done is that with the build scan and with the trade table scan, we are now able to read the data and use that data using for df.count or any of the aggregation from forward. So in last two sections, what we have done, so we are able to implement schema discovery. Now we are able to implement reading of the data. Okay. Now with the completion of reading of data, the next section we are going to look at is data type inference. So till now we only have done schema discovery, which means we have done the column names discovery, but all the column names or all the columns we are treating as a string as of now, which is okay for the beginning, but it's not great for so many things. For example, if you want to do aggregation on any specific column, if it's a string, you have to typecast everywhere, right? Which is not nice. So what we want is that we want to look at the data, not only first line, but maybe other lines, and understand what kind of a data it is. So most of the time, the CSV may have a string or double or integer, etc., etc. So in this section, what we are going to do is that we are going to implement the data type inference, so that rather than just using string everywhere, we can discover what are the data types of the actual columns. As we are done with the last two sections, we are going to check out the next branch or next tag which has that code. Okay, so what we are going to do now? So what we are going to do is that, so as of now we are treating everything as a string. So what we are going to do is that rather than taking a single line, we are going to sample the data, and for each of the row we are going to infer the schema. So what we are trying to do is that we say, okay, out of 100% of the data, take maybe 40%, and for each row infer the schema. Now this sampling is there for a reason to control how much data we have to look at in order to discover the schema. By default, the sampling ratio is 1.0, which means we look at all the data and discover the schema, but it may be problematic because if you have a huge amount of data, you may not want to run on all the data in order to see the schema, and also your rows may be homogeneous, which means by maybe looking at only few of the rows, we should be able to come up with the data types. So sample ratio is kind of a standard in most of the data sources, which allow you to kind of tune how much data has to be looked at in order to come up with the data type. So this is the one thing you may want to keep in mind. So what we do is that we take the inference, and here to make the implementation simpler, I have taken a shortcut, which means I take the sample, but whatever the schema given by the first row, which is not a header, will be taken. So I am not doing really the merge between multiple rows, because that needs a complicated implementation. If you want to look at the complicated implementation yourself, you can go to the JSON data source given by the Spark in order to understand how two different data types can be merged and those kind of things. Now, it's not only that we want to improve our schema discovery with the data types. Once we have the data types, we have to make sure that whenever we do the table scan, we give the right data types. Because as of now, when we convert in from an RDD of string to row, we are keeping everything as a string. But if we differentiate between different data types like integer and double, when we return the data, we have to cast it to right types, otherwise we'll get an error. So what we have to do is that we also have to improve the schema discovery and plus build scan in order to support data types. So what we are going to do is that, let us look at the first code, like how we are going to add the schema inference in the CSV relation. Right, okay. Okay, let us look at the schema implementation. Now, if you see this, so what I'm trying to do here? So what I'm trying to do here is that I'll get the same thing. Now I have a new option called sample ratio, which means I'm going to sample the RDD. Then for each RDD, I'm doing a different index. So index kind of gives me the allow to say which column I'm looking at. And for every field type, I'm calling something called infer field. Let us see what is exactly is infer field. Now the infer field is very simple implementation. What it does is that it takes a value which is of the type string and then tries to say what exactly is the type. So what I'm trying to do is very simple here. What I do here is first I'm trying to do, is it an integer? If it is, then I'll return an integer type. Otherwise I will say, is it a double? Then I'll return a double type. If it's not, then I'm going with the string type. So if you see here, again this is a very simple implementation where given a type, I'll just make sure that I try for integer. If it fails double, then otherwise string. So rather than sticking with string, then I will be able to get different data types. And if you see finally what I do is that whatever is inferred as the first thing, then I'll take and I'll use as a data type. So no more there's just a string data types in the schema. Now we can differentiate between integer, double and strings. Again, for your real purposes, you can improve this code to have much more diverse data types, but that's up to you. Now, as we improve that schema, we are also going to improve the build scan. So what we are going to do is that the first few lines remain same, but you have to focus on this line where we say data type equal to schema field index of data type, which means we get the data type of the given field, then we do a casting. So which means whatever there in the string, then we do a casting. And if you see the implementation of cast2, it's very simple. What we do is that whatever the data type we are specified in the schema, we just cast it. So if it is an integer, then we say value.toInt. If it is a string, we just return the value and those kind of things. So what we have done here is that we have improved the schema to have a different data types, and also once the schema is improved, we are also improved the build scan in order to use these data types information. Now what we can do here with this information, the first thing is that we're going to rerun the schema discovery to see that does it now have a new data types. Let us run this example of CSV schema discovery so that we know again the same parameters, there is no going to be different parameters here. Okay, let it compile. Okay, now it's running. Okay, we are running a CMS discovery like the first example. Now if you see the output, now no more we have a string. So we have integer, first three are integer, then we have a double. So which means not only we are discovering the column names, now we are also discovering the column types. Now with this information, and if you see the amount paid is a double, right? So which means we should be able to run aggregations. So we'll see one aggregation example also. So if you see this example, so I'm loading the same data. I want to aggregate amount paid. So this is a data frame DSL which allows you to do aggregations. So I'm saying is that df.aggregate, the column which I want to aggregate is amount paid, and the aggregation which I want to run is sum. The nice thing about this is that since we already know amount paid is a double by the schema discovery, we can directly run this aggregation without doing any casting. So let us see, does it going to work? Right, so this is the important part of the schema discovery and the type inference. So which means schema discovery allows you to have nice column names. Data types discovery allows you to have the right kind of aggregation functions to be applied for a thing rather than doing casting in the each part of the query or the aggregations. It's running. Let us see, do we get the sum ultimately? Yeah, finally we get the sum, whatever the sum of the data. So this kind of gives you the idea of how powerful this data type inference is, right? Okay, now let us start discussing about save as CSV file. So in last three sections we have discussed about how to do schema discovery, how to read the data, and how to do the data type inference. Now if you see our requirements, one of the requirement was take any data source and save it like a CSV file. In this section we are going to discuss about that. So as we are done for other sections, we are going to check out the code first. Okay, now we have a code. Let us continue. Now what we are trying to do here is that as we have SQL context load, we have something called SQL context save. Now when we try to save, as we had node entry point is default source, entry point to the save also is default source. So the default source should implement something called create table relation provider. So we have seen the relation provider and schema relation provider. Here we are seeing another trait called as create table relation provider. If you look at the name create table, kind of signifies that we are trying to save some data. Now again, since because of SQL, the naming conventions are using table. So what you have to do is that default source should implement create table relation provider, then it should override a create relationship. Now the implementation is very simple. What we do is that we take RDD of row, which may be constructed from any other data source, then we convert it to data RDD of string. So the idea here is that as we converted RDD of string to RDD of row for converting raw data into a structured data, now what we are going to do when we save the CSV, it's a normal text file. So what we are going to do is that convert RDD of row into RDD of string, then you will save as text file in order to save. So that's going to be the overall idea. So let us see the implementation now. So let us go into the full screen mode. Right. So if you see now default source also implementing create table relation provider. So with the schema relation provider and relation provider, now we also have create table relation provider. And also in the end we have create relationship which has SQL context. Now we have something new called save mode. We'll talk about that a little bit later. And also if you see in the end we also have data frame which is sent to us to be saved as a CSV file. So with including compared to other create relation functions, here we have save mode and we have data frame. Now what is a save mode? Now save mode is something specifies what to be done when there is a path exists. For example, if you think about Hadoop, whenever there is an output directly exists, normally we get an error. But that's not the way we want always. So what save mode allows us to do is that allows the user to specify what should be the behavior depending upon the things. Now, for example, let us see this implementation. What we do is that first we check for a path, and if path do not exist, if path is not specified, then we throw an error. That's very similar to the earlier code. Then we convert the path into file system path, because this path can be a HDFS path, S3 path, any path which is supported by Hadoop Express API. So we convert into a file system path. Then, depending upon the existence of the file path, for if it exists, then we look for the mode. So if the mode is append, so the user is trying to say append to the existing CSV file. But normally CSV files on top of HDFS do not support append. So what we kind of say is to the user that this data source do not support append. But if you are thinking about this data source like a JDBC, which is underneath using the RDBMS, it can support append. What it means that just add to the existing table. So that's what we are trying to do here. The second thing is that the same mode can be overwrite. Here overwrite means that just delete the existing file path so that we can save again. And the same mode can be error if exists, which means the user can say, I want to save it in this file path, but if it already exists, give an error, don't try to add. So these are the options we have. So in our data source, we support override or error if exists. So if the person says override, then you override. If the user says error if exists, then we give an error. So that's kind of a way of using save mode. Then once we say, okay, we are ready to save, then we call save as a CSV file. So let us see what actually is save as a CSV file is doing. It's very simple actually. What we do is that the first implementation detail here is that first we get the header from the data frame.columns. So from whatever the data frame is sent to us, we just say columns, which will give us a list of columns. Then we say make string, so we'll get a header with a comma separated one. So here what we are trying to do is that when we save the CSV file, we also want to write header with it. The reason is that maybe if this data going to be input to the another Spark program, we want to have this schema discovery. So if we don't write the header, we cannot do the schema discovery. So for that reason, so we want to write the header. So now how we are going to implement is that we want to write the header once for a partition, because for every partition we know Spark is going to write one file. So what we want to do is that rather than embedding the header in only one time, so we want to embed in the other partition. So whichever the partition Spark takes, I should be able to do the schema discovery. So that's why what we are doing is that rather than using a map, we are using a map partition here. So then, as you know, the map partition normally returns a iterator. So here we should be able to return an iterator of string, because ultimately we want to convert RDD of row into RDD of string. So we take an iterator, we keep around a variable called first row, we'll discuss a bit later. Then we say has next. So the main important part is next. So what we here do is that we take the iterator which is on the RDD of row. Then what we do is that we convert into a row value by just going over it and converting into two strings. So here there is nothing much, but once the row values are there, we create a line by using a comma separation, but the actual part is in this if condition. So what we are doing here is we are trying to say if first row is true, which means we have not yet written the row, then what we do is that we write the header, then we put the row. So which means the first row has to be always the header, then has to be the actual row. If it is not, then we'll just put the row. So that's the only the difference. What we are trying to do is here, if the first row is not written, then we'll write the header, then we'll write the row. If it's already header is written, then we don't care. And if we have an empty partition, we will still write the header so that it will help us to do the schema discovery. So overall, what we are here trying to do in this implementation is we first take the save mode. Depending upon save mode, we process it. Then once the save mode says we can save the data, then we will take the RDD of row and convert it to RDD of string. And ultimately, once we have RDD of string, we use rdd.save as text file in order to save it to the HDFS file. So this is overall the implementation of save thing. Now we can also execute this program. Here we have a CSV save example. So if you see here, So what we are trying to do is that as we create a DF. Now what happens is that if we create a DF from the CSV and again save it to CSV, then it did not look nice. So what we have done here is that I have created a data frame from a JSON file. So using a SQL context load with a built-in JSON support, then I'm taking that JSON data frame and trying to save it as a CSV file. Let us look at the JSON before we run. So we have this sales JSON which has the same data as sales.csv but in the JSON format. So we can run this example. So what we do is that let us see what are the parameters you should send to it. Right. So you should send local, that is the normal thing. So rather than sending the CSV, we are sending the JSON file because we want to create a data frame from the JSON and we want to create the things from sales.json. And the third parameter should be the path where the CSV file has to be saved. So here I am saying /tmp/output. You can choose whatever the one you want. So what we do is that before we run, we just make sure that do we have /tmp/output. So we don't have a /tmp/output. Now what we want to do is that we are going to run this program. One more thing. So just to make sure that you understand, so we have a df.save, same information and the path. So let us run this code and see is it going to save the file. I can give some seconds for it to compile so that we have the running code. Okay, it's executing now. So it's completed the execution. Let us see what is the output it has written. So we have a file now. So let us open this file and see. So if you see, now the file is written as a CSV file. So what we have seen here is that we took a data frame as which is in the JSON format, then we convert it to CSV and save as a file. So to save as a file, the default source should implement create table relation provider and convert RDD of row into RDD of string. So next step is column pruning. So the next two APIs, whatever we are going to discuss, are going to be a little bit advanced than what we have seen earlier. So till now we have seen schema discovery, then we have seen how to read the data, then we have looked at data type inference, then finally we looked at same things. Right, so these are normally mandatory for any kind of a data source. But next two APIs, they are not really mandatory. So they are more of a performance benefit. So which means when you start with the data source, you implement the first flow so that you have things working. Then once you have all things working, then you can optimize your data source to have a better and better performance. So the next two things we are going to discuss are the one which are for performance benefit. So what is a column pruning? So as we did with the other things, let us first get the code. Okay, so we have a new branch and a new code. So what is column pruning? To implement column pruning, we have to implement something called PrunedScan. Now if you remember, we implemented something called table scan in order to be able to read the full data. Now what is new about PrunedScan is that it allows us to select only the columns which are required. So like a table scan, so table scan says get me all the data. PrunedScan is that get all the data with specific columns. So it's kind of a saying optimize for only few columns. So what PrunedScan does is PrunedScan gives the information to the data source which columns it wants to access. So this is given by the Spark SQL, and this information will be passed to the data source in order to say, oh, only these columns are needed, you don't need to read everything else. So what we do is that when we build RDD of row, we only put the columns which are needed rather than selecting all the columns. One caveat here is that there is no performance benefit in the CSV data, because this information we cannot push it to the disk and say only load the columns, because CSV data is a normal text file which do not have that kind of facility. So here the code is just shown you to understand how to implement this kind of API. So but you don't get real performance benefit. But if you think about data sources like JDBC, where you can push the column information to the JDBC server, and it can do only the few columns to select, so that you only get so many columns. So you have to remember, this is a performance benefit not for a CSV data source, but for the data sources which can only load few columns like JDBC, Parquet and those kind of things. But this example gives you the idea what's going on. So let us look at the example. Before that, we'll look at the library improvements. So we go to CSV relation, and if you go to the top, you see that we are now implementing PrunedScan. So what we are doing is that we are not only implementing table scan, we are also implementing PrunedScan. Now what happens is that now we have two build scan, one build scan for table scan and one build scan PrunedScan. First build scan do not take any parameters, that's what we saw before. So what we do is that we call the build scan another build scan with just all the fields. So the default build scan is take all the fields. But another build scan is that we get a build scan with the required column. So what happens is that when we only select few of the things, then this information is given to us. Now what we have done here is that we have added a logger, so such a way that whenever there is the columns are selected, we will get to know. So most of the implementation is same, but only thing is what we have done here special is that whenever we pass the information back from RDDF string to RDDF row, we check is the column is in the required columns. If it is there, then we will select. If not, we don't select. So these are only the things we are doing different here. So what we have seen here is that whenever there is a columns are selected, so how columns are selected we will see when we run an example. We will make sure that when we convert from RDDF string to RDDF row, we only select those columns. And how we do it? By implementing the PrunedScan. So let us see, we are going to use the same example of sales sum, because if you see here, we are going to select only amount paid to do the sum, because we don't need any other columns. We are only going to create a data frame with the amount paid, and from the logger we should be able to recognize that. So let us run this example. Now this example is running against this PrunedScan compared to the table scan what we had earlier. Now the example is running. So this is the same sum example what we have seen before. We should get the same sum, but only the interesting part will be is we will have the columns only selected for amount paid rather than actually selecting the all the columns which are there in the CSV file. So let us look for that our loggers. So if you see here, it says pruned build scan for column list amount paid. So it kind of showing you that this pruned scan is called with only one column. So this is very good for the data sources which allow you to only select columns rather than selecting all the columns. So as I told you before, this is one optimization technique. After your data source is ready, you can implement the pruned scan so that you only select the columns which are required. So with the similar to PrunedScan, there is another technique we can use for performance. This one is called as filter push, or also we call this as a predicate push. So here idea is that not only we send the information which columns we require, we also push the information that which rows are required, so that we don't need to load all the data. So let us check out the next branch so that we can look at the code. Okay, so we have a next branch. So what you have to do when you want to do filter push? As we had PrunedScan, so we have another try to implement by name called PrunedFilterScan. So now not only we get the column information, we also get the filter information. So the filter information means if you are filtering by where class or join or something, then this kind of information will be pushed into the data source. Now what we do is that as we selected the columns in the RDDF row, now when we return RDDF row, we only give you the rows which satisfy the filter. So if you given a filter, we only load the data which has a filter. It's an optimization. Now there is one trivia here, so you have to remember. One thing as of now Spark does is that even if you applied the filters in the data source level, they will be reapplied when you run the RDD. The reason is that this is just an optimization. So the filter is only done in order to reduce the amount of data loaded, but the filter will be again run as part of the RDD evaluation. So it's just an optimization. Even if you do not implement that in the data source, anyway the filter will be done for you. So this is a trivia I want. So even though my code do not implement the filter, you still get the filtering thing. The reason is that since it's an optimization, even if you don't implement real filtering, you still do the filtering. So in my code, since the filtering logic is a little bit difficult, I have left it for the viewers to implement themselves. I will show you the skeleton of code which you have to implement what's going on. So in the CSV relationship, let me get into the full screen mode. You can see another build scan which is coming from, okay, so PrunedFilterScan. As I have PrunedScan, I have a PrunedFilterScan. And if you see, I'm just putting a logger just to get an idea that what are the filters we are getting. So as we got array of columns in the build scan of the PrunedScan, here with the array of columns, we are still again getting filters because we are implementing the PrunedFilterScan. So here I am just logging, and once I am logging, I am just sending the required columns to the build scan. But here you can have your own code which pushes these filters back to the maybe JDBC or whatever it is in order to get the better optimization. Just to show you that this works, so I have an example of CSV filter example where I am filtering amount paid by 500. So any amount which is greater than 500, I want to have them as the rows. So again, here idea here is that I should get this amount paid greater than 500 as a filter in when I'm executing it. So as of now, I'm not doing anything, which means the Spark is doing actual filtering. But if you have a data source which can do actual filtering, you should be able to use this API. So now it's running. It's the same parameters what you have set for other things, so local and CSV. I will be getting the number of rows less than 14 because we are filtering on some data. Now what I am interested is that I want to see that logger and see what kind of filter I am getting there. Okay, let it complete. So here I am getting 3 rows. Now if you search for PrunedScan, you can see here that it says PrunedBuildScan for column list with the filter. So you get a filter specified called as greater than, amount paid and 500. So filter has a name, that's a greater than. It has a field, which field I'm specifying, and the field value. So by this you can do the filtering things. So what we have seen in this example is that you can implement column pruning and filter pruning in filter and push in order to have a better performance. So in the last 1.5 hour sessions, so what we have looked at is that how to create a data source from the scratch. So the idea here is that data source API allows you to work with structured data so that you can load and save into a different sources, and creating your own data source allows you to plug into any custom source that has possibly there inside your organizations. I hope you enjoyed the session as much as I do. Thank you for listening.